Okay, so today we have video recording and voice recording, and I will probably publish this on YouTube either tonight or tomorrow morning with the password, so it's not like everyone can access, but you know. And now let's begin. So last time we start talking about this two-level system, an atom or molecule, whatever, and then you have a light incoming, has amplitude, and then cosine omega t. Omega is frequency of the light. And then we have the ground state, its energy is E1. The excited state, the energy is E2. Okay. And also we can define delta E, the energy difference between E1 and E2 corresponds to a frequency. Okay. And we know that, last time we know that to solve the state of the atom, we can write down the function, or the wave function, the state, as a linear combination between state 1 and state 2. Let's say initially if there's no light, then the atom should be in ground state. So AT is 0. Sorry, AT is 1 and BT is 0. Okay. The idea is to solve A and B when there is light. And the way to solve it is use Schrodinger equation. Okay, the way to use Schrodinger equation, and then we also talk about the Schrodinger equation. The Hamiltonian can be written down as the original Hamiltonian of the atom. It's like when there's no light. And then a term that is the potential energy of the electron in the electrical field of the light. Okay. Q times E is a force times X is a distance, so that's the potential energy, just like a static electrical field. Now, when you first look at this, there's a huge disconnect between, so you want to plug this and this in here, but then they're somehow written in different language. Okay, the wave function is written in 1 and 2, and then the Hamiltonian is written in some letters, something you don't know. So the first thing we want to do is to figure out what's H knob. H knob you can write down, like hydrogen atom, you can do these complicated things, but the most straightforward thing is H knob, when you hit with the ground state, it gives you E1 ground state. Okay, so this is the eigenstate condition. You have eigenstate. Ground state 1 is the eigenstate of the atom. So you do this, you get E1. And also you have this, you get E2. Okay. And I think that is all we know. Now, the next thing we want to do is a little bit tricky if you look at it for the first time. But this is something really, really common in quantum mechanics, is to do what we call a projection. Okay? We want to project H into a space created by the set 1 and 2. Oh, yeah, sorry. One more thing I want to cover here is if you do the inner product of 1, this one is 1, also this is also 1, and then okay, orthonormal condition. Okay, there's something in common, common for all the quantum mechanics problem. So the next thing we want to do is we actually know something about this 1 and 2, right? You now know H0 here on 1, and also you know when they to do inner product. And then the third thing I think we should mention here is we assume the function is known, the solution is known. Let's say for hydrogen atom, okay, people already solve it, so you know the real function here. Okay, you can write down its form. I believe it has something very complicated here. You already know the form. So what this means is that if you do this, let's say I x j equals okay, this number, we can calculate it. We can calculate this number for your atom or for your molecule, simply because we can use some software or we can do whatever to know the solution to this I. Okay. So this is, I think this is it. This is all the things we know to this problem, and now we can start to solve it. Okay. So whenever you see something like this, the first thing you can do is to make projection. The projection of something called expression. It's to project your Hamiltonian to the space created by this 1 and 2, created by these eigenvectors. Because once you express H as 1 and 2, then when you multiply H and this, right, when you multiply these two together, you have a set of rules you can use. Like if it's H0, then times 1 you get E1. Okay, if 1 times 1 you get 1, 1 times 2 is 0. And then this number is also known. So you have a set of rules you can use to calculate what this part really is. Okay, this part is relatively simple. You just take the derivative. Okay. So this is a projection. So the way to do projection is actually a standard way. We know last time we already introduced there's identity matrix. Identity matrix, its property is whatever you multiply it, it's just 1. Typically it's 1, but it's a 1 in a different form. Okay, so in quantum mechanics, we can say I is a sum of all the eigenvectors. Sum of all the eigenvectors, and then written in this. Okay, left bracket, right bracket, and left bracket in this order. Cannot reverse. Okay, in this order. And we have for our system, because our eigenvector is 1 and 2. So in our system, we have 1 plus 2. Okay, this is our identity matrix. If you don't believe it, you can give it a try, right? I times 1 equals 1, 1, 1 plus 2, 2, 1, right? You give it a try. This is 0. This is 1. You get this. Okay. So this is identity matrix. So now the common thing you can do to your system, it's always this I, H, I. Okay. You can always do this because it's identity matrix. You multiply one on the left, and you multiply one on the right. And what you get is, let's first take a look at each knob. Okay, we do it part by part. Okay, this part is easier. This part is more complicated. So we do each knob first. I, H, knob, I. And what you get is 1, 2, and then your H knob, 1, 2. Okay. And then now you can calculate this. You do H hit on this, so H hit on this. Okay. And we use a rule we already know here. These are the eigenstate. So here I will go a little slow. Some people might already know the answer, but just be patient, because some of you might be the first time to see this. This one hit this one, get E1, 1, 1 plus E2, 2, 2. Okay. And E1, E2 are numbers. You can just put it in the front. Now you do this multiplication, right? Product. And what you get is this times this. Okay. This times this is 1 inner product with 1. So you write this down. I'll do it a little bit slower. Put the E1 first. It's a number. Then here, 1, 1. Here, 1, 1. Okay, this is the first term we get. And this term, we know 1 inner product with 1 is 1. Okay. So this term goes to E1. This term goes to E1, 1, 1. Okay. So inner product is 1, so you combine these two, it becomes like this. And then the same apply to 2 and 2, right? These two terms. And you will get exactly the same thing, 2 and 2 here. Now, what about this times with this? This times with this, you get E1, 2, 2, 1, 1. Right? These two terms times together, and you get this little thing here. This one we know from our orthonormal. This one is 0. Okay? It means two eigenstates, they are orthonormal to each other. So this one is 0. So is this term multiplied with this term. Okay? So we finished all 4 terms, and then we're left with 2 non-zero terms. And we can actually write down the other one. 0, 1, 2 plus 0, 2, 1. Okay, they're just 0. We can still leave it here. Now this one, you can actually directly use it now, because when you now hit H with your wave function, the only thing you do is you do this inner product between 1 and 1 or 1 and 2. So you already can know it's either 1 or 0. Okay? But there's a better way, or more straightforward way, or easier way to picture this. So notice the label here. It's always 1 and 2, and then but they have an order. It's either 1 1 2 2 1 2 or 2 1. I don't know if this remind you of anything, but if you have a 2 by 2 matrix, your 2 by 2 matrix have 4 components. Okay, have 4 components. So this one actually can be written in a matrix. And the reason we use matrix is because it's related to linear algebra, and there's a lot of mathematical tool we can do. Okay, and in a lot of ways, it's easier to write down a matrix other than repeating all these labels here. So from here, we can write down H knob equals, okay, you have 1 1 is E1, 1 2 is 0, 2 1 is 0, 2 2 is E2. Okay, so you get a matrix form of your Hamiltonian H knob. Now let's write this down here. And then let's see. The beauty of this is that you don't have to worry about what is 1 and what is 2. Okay, you don't have to worry about their physical. You don't have to worry about their actual. Let's see, do I need this? And because now the matrix, well, the Hamiltonian is in matrix form, we can think about how to write down our wave function. Okay. You have, so I'll just give you the answer. One is, because the Hamiltonian is it's a vector multiplied by a vector become a matrix, and then the vector is just a vector. So you can actually write it down as this. Okay. They are eigenvectors. And it's easy to show that when these two, so first when they do this, it's easy to show it's 0. Okay, because what you're typically doing is you take this, you do a dagger times with this. This gives you 1 0 times 0 1. Okay, is 0. Okay. So left bracket, you just rotate it. And also, what this tells you is that you need to verify this, right? What is this? If you write down in the matrix form, you have E1 0 0 E2 times 1 0. Okay. And this one, first row, first column, second row, second column. First row, first column, you get E1. Second row, second column, you get 0 E1 0. Okay, so this is just to show that you can simplify this probably will be a bit conceptual things into a matrix and a vector that you can try to solve. Okay. Now, so this is the easy part, H knob. Now let's do the other part, this one. Okay. So because these two are independent, you can actually write it down. You can just switch the order. Normally you can't do that in quantum mechanics, but this one is fine. Okay, just switch them. And this one equals so notice this is because, let's see. No, I should put this here. So because this Q is a number, you can just move it around. And E is an external field, it's just a vector. And it's not something from the atom, so you don't have to worry about it. You can also treat it as a number, okay? And you do I, Q, X, I, right? Just the same as how we do with H. And now what happened is you can see again, we do this 1, 1, 2, 2. Let's erase this side. One, 1, 2, 2, Q, X. And then 1, 1, 2, 2. Okay. And previously we say we know what is 1 and what is 2, their actual function. So you can now go as first term here. Okay, you get Q. It's a number. You put it in the front. I'll do the first one in detail, and then you can see the rest. So 1, 1, X, 1, 1. Okay, this is the first term. And what is this? This is, write it down here. 1, X, 1, by definition, how we define this inner product last week, it's 1, okay. By definition, it's this. And also by definition, this one is the average value of X in state 1. Okay. So this inner product actually becomes a number because inner product you already do this integral and becomes a number or become a vector. Okay, if we want to be more a number with direction, if we want to be more specific. So what we can do is we can move this in the front because it's a number now. So we get minus E. Let's move the Q out first. And we know it's X, 1, 1. It's a expected value or average value for X when you do this inner product of 1 and 1, okay, here. And you're left with, again, 1, 1. Very familiar, right? This is a matrix form now, would be. And you do the rest, it's all the same. So you get 2, 2, 2, 2, plus 1, 2, 1, 2, plus 2, 1, 2, 1. Okay. Again, this helps us to write something down in a matrix form. Okay. Exactly the same treatment. Actually, you can do this again and again for any system as long as you know 1 and 2. Okay. Now, the next part is a little bit tricky. What is this? 1 and 1. Average value of an atom in ground state, its average position. What is the average position? Make a guess. We have atom here, the core, and then electron orbiting around. The average value is 0. Does it make sense? Right? The probability of finding it on the plus side is the same as finding it on the left side, right? Minus sign, because it's spherical symmetry. Okay. So the average value. So make it very clear here. This one is 0, but this one is not 0. Okay. We're not saying the atom is at the center. We're not saying the molecule is at the center. We're not saying that. We're just saying because this has direction left and right, so that it's 0. But if you think about where it actually is, if you give it a square, okay, you remove that direction, then you get a non-zero thing. Okay, so this is, although this is 0, it doesn't mean the electron is at the center. Okay. So this one is 0. This one is also 0. Okay. For all the eigenstate for a very simple atom, it's 0. Okay. Maybe there's some special case it's not 0 when you break the symmetry, but it's in this class we don't really care about those. Okay. And the next thing, we further simplify our equation by making a definition. We know in the past we know that the polarization is the number of atoms, number density of your atoms times the charge per atom times the position. Okay, how much you deviate from 0, and R is actually it's 0. They're all the same. It's just a label. So we can actually define this as a dipole. It's a dipole. It's a polarization per atom. Okay, it's a dipole. The reason we do this is because we happen to have Q here, and we happen to have X here. Okay, so it just makes sense to get rid of this. So this is now the definition. I, Q, X, J. Definition. Dipole I, J. Okay, it's a vector. This is a number with direction. Okay, it's not an operator. So now we put this to replace this and this, and what we get is minus E cosine omega t Q X equals to minus E cosine omega t mu 1, 2, 1, 2 times mu 2, 1, 2, 1. Okay. And for simplicity in this class, we yes, shuts down. Okay. Yeah, so unfortunately this is a camera, it's not a video recorder, so it has a 30 minutes limit. Okay, is it started? Good, okay. And for this class, for simplicity, okay, we stay in the case where mu 1, 2 equals mu 2, 1. This is just a very weak assumption used in this class. It's not true for a lot of atoms. Okay, we just want to simplify our life a little bit. Now when you combine these two together, H, now you get E1 1 1 plus E2 2 2, okay, and then minus one, 2, two, 1. Okay. And the matrix form, it's simpler. We don't need to carry all this. It's E1, E2, as before. And then we have this off-diagonal term. Okay. Okay. So this is how we write down the Hamiltonian in the space. We call it space, or Hilbert space, created by the eigenvector 1 and 2. Okay. And we can express this space in a matrix form. Okay. Any questions so far? Okay. And the next step is, well, since we already do this, let's do let's do the wave function. So, theoretically, you can already multiply this with this. Okay, you can already do that. It's all there. 1 times 2, or all this inner product is either 0 or 1, so you can already use this for calculation. But I don't want to carry all this, and then also in a lot of papers, people don't write it in this way. They write it in a matrix form because it's simpler. So we need to write down the wave factor, wave function in a vector form, right? A, T, 1, B, T, 2. And we know 1 is 1, 0. 2 is 0, 1. Right? We know this. Showing here. And then we get Okay. So this is our wave function now. Well, the pace is a little fast. We might finish early today. Okay. Now let's do Schrodinger equation. H wave vector equals okay. So you have E1 mu1 2 E cosine omega t mu 2 1 E cosine omega t E2 times A B equals okay H phi okay equals this side I H time derivative okay, and this well, this one we know how to do, right? First row, first column, second row, second column. It gives you E1 AT minus mu 1 2 E cosine omega t. Well, if you're tired of writing mu 1 2 times E and cosine omega t, later we'll replace it, but it's not there yet. Okay, times Bt. Okay. The second row column is okay minus mu 2 1 E cosine omega t Bt. Sorry, AT. Plus E2 Bt equals this. The dot means differential in time. Okay. And this, any problem? Okay. So this Schrodinger equation are now converted into a vector equals a vector. Okay. And we all know a solution, right? The vector equals vector means all the components have to equal to each other. So here we will have I H, the time derivative of t equals E1 AT minus mu 1 2 E cosine omega t Bt. So that's the first equation. The second one, these two numbers is the same. IH Bt equals E2 Bt as mu 2 1 okay. So finally we get something where I think everyone should be familiar with. Okay, a set of equations about A and B, and A and B is not some complicated functions. A and B are numbers that change with time. Okay, as simple as that. And when you look at this type of equation, they usually have a name. It's called coupled equation, right? Because let's say at first you're in A, ground state. A is 1, B is 0. So what A can do is that it can create a term here to make the time derivative of B non-zero. So now your B start to grow, okay? And then when B start to grow, you in turn change the growth, the rate of change of A, okay? So this is a couple mode equation that is very common in two-level systems. And the next step is a little bit, it's also very common, but it's not really that necessary, but we would do it anyway, is to get rid of this. This one is kind of a little bit annoying. And if you're familiar with quantum mechanics, you already know you can do this by what we call rotation frame. Okay. So what we do here is you take AT equals a slow varying components and the fast oscillation components, EIT divided by h bar. So EI divided by h bar is if you remember, would be the frequency of your state. Okay, your state has a certain energy, so you have a wavelength. You also have a frequency. Okay, so this is called rotation frame. We can do the same to B. Okay, this is always the case when you see the first derivative over t, and then a linear term, and then they have an I. Okay, any equation you see this, you can do this. Okay, it just works. It doesn't necessarily need to be in quantum mechanics, like in a lot of. Let's see if the radio. Okay, good. So for a lot of other type of equations, we always run into this. You can imagine for light, it has a frequency, so you run into this. For anything have a frequency, you kind of will run into this. And now let's put this back in here. Okay. Derivative of this gives you IH. Derivative on this minus I, derivative of this side, E1 H bar. Okay, left hand side, derivative on this, and then derivative on this. Okay, and you can see when these two times together, it gives you E1. Okay. And the right hand side, we have E1 A T E minus I E1 T H bar minus mu 1 2 E cosine omega t and B E. Okay. So we already say this term equals this term. Okay, when you multiply this, it just gives you E1. You cancel them. And then you're left with this. So this one, you can move this rotation part to this side. You can also move RH bar to this side. Okay, you can do those. And you end up with I mu 1 2 E cosine omega t bar. Okay, and then bt. Okay, and then E minus I E2 E1 T H bar. Okay, you move this one to this side. And this one, we already know, defines as the frequency of your transition, okay, between these two modes. So you can actually move this as okay. And if you think about it, this term, this equation makes much more sense than the original equation here. The reason is, for our system, think about it. If we raise E1 and E2 by the same level, okay, let's say by any energy, you raise it by the same level, it actually doesn't affect you, okay, because how you define energy zero is a relative thing, okay. So instead of having E1 and E2 hanging all around everywhere, their difference is really the thing that determines your system, okay. And then, so let's write down here H bar omega. Okay. And next one, we can do the same thing to this equation. I wouldn't repeat the same calculation, but you can kind of guess the answer already. This equation has a very good symmetry, right? You replace A and B, 1 and 2, the label, it's identical. So you do the same thing here. Bt equals I switch 1 and 2. Okay. Cosine omega t bt switch A and B. And here, because we switch 1 and 2, so there's a minus sign here. Okay. So I think let's write it down this so we can move it later. Okay. Yes?
A is minus I omega t. B is I omega
t. Which equation?
You already have a minus sign after the A function e to the negative I omega t.
Oh, okay.
So this means B should have a positive sign.
C. Wait, no. Here you're doing, right?
E2 minus.
So this one is E2 minus E1, right?
Yes.
And for the equation of B, it should be E1 minus E2, right?
Yeah.
So you get, right? So you get plus sign, right?
Yeah.
Oh, okay, I see. Yeah. Get it reversed here. Okay. Okay. So when you look at this equation, the first thing you don't like is cosine, right? It looks so awkward there. Okay. And so standard way again, this is just math. Sometimes you have to do them. And hopefully one day Mathematica will be so great then we don't have to do it anymore. I think Mathematica actually can do some kind of this calculation, but something they get stuck is that they will give you solutions like this instead of going one step further, because to them, for a computer, it's really the same thing. To us, it's different. Okay, so you can do this, very standard, and multiply this with this, you get something interesting. Let's see which part we should erase. Okay, probably here. So let's do this first, and then let's do the A first. Okay. Two comes here, BT. And then we have these two times together, minus I, omega minus omega t, plus E minus I, omega plus omega t. Okay. And here's the first approximation we'll do. From this semi-classical picture, we call this semi-classical because the light is classic. For this semi-classical picture, what we do is that when you look at this equation, and these two frequencies, they are actually very different, okay? Because we're discussing about light. So for light, let's say for visible light, the frequency is about 400 terahertz, okay, very fast. And then when we have an atom, this is, let's say, F. This is absorption. So when we have an atom, the energy level, when it's sitting at omega, it always has a little bit of line width, right? Let's say you have heat it up and it start to collide with each other. This is called Doppler broadening of your spectrum. So you always have a little bit spectrum width. And for molecules and atoms at room temperature and atmosphere pressure, these two are important. If you cool them down, this can be really narrow. Okay, so for the regular temperature, regular pressure, this delta, the line width, is about gigahertz. Okay, it's about gigahertz. So there's 5 to 6 orders of magnitude difference here. So it means, let's say we want our atom to absorb our light, right? That's why we do it. We don't want to put the laser far away. So let's say we put our laser here, omega. So in this case, omega minus capital omega minus small omega will be something around gigahertz range or even smaller. So it's relatively a slow thing. Okay. This one is probably 1,000 terahertz almost. It's very, very fast. So when you look at this equation, there are several ways you can make this approximation. But what happens is sometimes people just, well, one straightforward way is that we want to know A in a long time scale, the scale, a gigahertz scale, like nanosecond. Because if you're really doing this 100 terahertz is femtosecond, we can't even see it. Our electronic stuff cannot track it. So they just get this to 0. Because you're just doing a very fast oscillation, that if you solve your A, if it's something like this, the envelope is coming from this term. And then this term simply give you all those oscillation inside. Okay. And it's very, very fast. So, and for us, we just want to know, like say, want to know the probability of your atoms in ground state or in upper level state. So we don't really care about this very small oscillation. And the other way to do it is simply write down the solution of AT. Okay, it's a derivative of t. Then you can do integration. Okay. You can do this, right? And let's say this one, this phase term move from 0 to half pi. That probably give you a number, right? Let's say you integral from one to another, it gives you a number. But at the same time, this one has already gone through probably 1 million cycle. Okay, so it will appear as a random number. It really depends on some number, how you choose the t, and the t, to a very small part that even doesn't affect this, it will affect a lot of this. So on this end, people just take average, and this average, you approach 0. Sometimes it's positive, sometimes negative. Okay, and unfortunately, neither of this approximation is correct. Okay, this explanation is, I would say, it's just nonsense. Okay, because if you go through a quantum picture, it will make much more sense. The term associated with this refers to your atom absorb one photon, and then move from upper state to lower state. So the energy simply doesn't conserve, right? You lose the photon energy, and then you also lose your atom energy. It just doesn't conserve. You violate the energy conservation law. So this term is very clear in a full quantum picture, but unfortunately in semi-classical picture, it's not that clear. And you may argue why it matters. It matters when you go into microwave regime, because in microwave, these two are very close. Okay, you just have a gigahertz, and then the difference could be gigahertz as well. Okay, there you cannot use semi-classical way to argue this is much faster than this, and you get rid of it. But in a quantum picture, you can always get rid of this because it doesn't make sense. Okay, so this is the approximation we use in light frequency, in optical frequency. It's called rotation wave approximation. Okay, but what it really is energy conservation. Okay, see now. So we somehow simplify it, okay, by getting rid of this term. Then you now arrive at I 1, 2, E H bar 2, right? I think there's 2, yes. And then E okay, and then you have, sorry. So this looks much, much better. And then starting from here, okay. And next we want to make some definition to further simplify this. Just want to make sure it's correct. Okay, we define detuning. Okay, we define the laser frequency minus the resonance frequency as detuning frequency, the frequency difference between these two systems. And then we also define, this one is fun, this is called Rabi frequency, okay, discovered by Rabi, and I think Rabi is also one of our price as mu 1, 2. Okay, just definition. And it's interesting that 2 is still there. Okay, later you will see why in Rabi frequency we didn't include 2. And this Rabi frequency, the definition is related to a frequency about how the frequency of how the atom is flipped from ground state to upper state and upper state back to ground state. Okay. So these are the definition. And then another thing we do is that we don't like this tilt. Okay, carrying around is a little bit stupid. Okay, so we think about like how we write down our wave function. We do it as a t tilt e minus I e1 t h bar plus, okay. This part is the original A. Okay. Okay. And for simplicity, because from this equation, you really don't need to know this. Okay, you just need this. It's enough, right? So you remove the tilt. Okay, from now on, A is this. The definition is coming from your wave function. Okay. So we arrive at something relatively simple, still difficult to solve, as okay, A I Rabi frequency divided by 2 E, okay, here I think it's plus sign, C just double check it's the same notation as mine. There's a minus sign difference here. Okay. Let's leave it this way. Thinking should be correct. Okay. So this is the equation that looks simple enough to solve. Okay. And actually, if you try to solve it, it's still hard. You need to do again a rotation frame, and then the math goes on and on and on. So here we will simply set the simplest case on resonance condition. Okay, you set this on resonance to get rid of this part. In experiment, it's possible. You just move your laser frequency. Okay, you move your laser frequency to be the same as your transition frequency of your atom, and you reach at this condition. So it's doable. And the equation finally becomes something everybody can solve. Okay, becomes like this. And this is a standard oscillation equations. Okay. And what you do is that this coupled equation, what you do is you want to replace B with this equation. Okay. And the way to do it, we already did it once in the Maxwell equation. You take another time derivative on this equation, and then it gives you minus IR2 B derivative. B comes in as minus 4. Okay. And the solution, universal solution to this, there's a cosine 2 omega RT. Also there's sine omega RT. Right? You do one derivative, you come down omega R divided by 2, and then you do it again, you come down again, and then there's a minus sign, okay, when you go from cosine to sine. So this is the universal solutions. So you can write down AT equals to coefficient C1 cosine 2 plus C2 sine. Okay. So linear combination between these two general solutions. And then you can also get B, right? The derivative of A gives you B. Okay, so BT equals C2 I omega R. Just move I. Okay. And then you do this derivative, you get minus C1 cosine omega R divided by 2 sine 2 omega RT. C, okay, plus 2 omega r C2 cosine okay, you cancel this, right? And then it gives you I C1 sine minus I C2 cosine. Okay, so you now get the solution of A and B. The only thing we need is now is the initial condition, right? Initially, let's say the atom is in the ground state, so it's easier that way. Ground state, then you have AT equals 1, B equals 0. Okay. And what it tells you is that at time 0, this one is 1, this is 0, so you have C1 equals 1. And you don't know what C2 is, so you look at this. BT should be 0 at time 0. This is 0, this is not 0. You want it to be 0, so C2 is 0. So now you get your solution as AT equals cosine omega r 2t BT equals I sine omega r t. And this is well, I want to finish this, so probably will be late for 2 more minutes. Apologize for that. Now I want to know the probability of in one ground state and in excited state. So the probability of in ground state AT squared d, right, equals cosine square, okay, and then gosh, I hope my math is a little better. So this one goes to 2 half cosine omega RT. Okay, a little bit embarrassing. And then the probability in excited state becomes BT squared sine, okay, equals 1 minus sine. So this is why the Rabi frequency, we didn't absorb a 2 there, okay? Because the probability is oscillating at a frequency of omega r, the Rabi frequency. And what this means, this is something, get back to the Einstein, how we helped him to figure out why the B coefficient is identical, okay? So what this means is that if you write down, this is T, and this is your ground state probability. Yes. Oh yeah, you're right. Okay, thank you. So you start from 1, and then you oscillate to 0, okay? And you go back, and you do this. So you're doing oscillation. The atom is going from 0 to 2 to 1 to 2, 2 to 1 again. And so for the P2, doing the reverse. Okay. Okay, this is P2. And this part, when atom is moving from ground state to upper state, represent absorption, right? You have energy into your atom. So this part, absorption. And this part, you have your energy moving from upper state to lower state. So this part is emission. So you now see absorption and stimulated emission are the same process. Okay, they just have a minus sign there. Okay, up and down. So this is why in Einstein's model B12, I think it's B21, their coefficient, the stimulated emission coefficient is the same as the absorption coefficient. Okay, so this is for this class. Okay, thank you.